This video is on conditional statements. So these are expressions of the form if P is true, then Q is true, or P implies Q. So if P and Q are each statements or open sentences, then the expression if P then Q is a statement. And it can be written in this way. It can be written as P implies Q. It can also be written as this sort of arrow with two lines, P implies Q. So this will be our symbol for P implies Q. So as an example, let's let P be the open sentence, X is an integer multiple of 10, and let's let Q be the open sentence, X is an even integer. Now notice that neither of those are statements by themselves because each of them depends on the value of X. So for example, if X is 20, then P and Q are both true, and so on. But if X is 1, then neither P nor Q is true. So let's think about whether the expression P implies Q is true in this particular case for this P and this Q, and whether Q implies P is true, again, for this P and Q. So I'd like to just pause for a moment and let you think about those. Okay, so if P is true, if X is an integer multiple of 10, is it necessarily the case that X is an even integer? Yes, this will always be true. So if X is 10 times some other integer K, then we could also write that as 2 times 5 times K, where this is an integer. And so, yeah, if X is an integer multiple of 10, then X will also be even. So anytime that P is true, Q will also be true. So this overall is a true statement. P implies Q is a true statement. Is Q implies P a true statement? Well, sometimes, for some X, it's the case that X is even and X is an integer multiple of 10, but it's not always the case, right? So, let's say that X is 4, then X is even, but X is not equal to 10 times any integer for K in the integers. So this was true, this was false, and there are situations in which X can be an even integer, but X is not an integer multiple of 10. There are situations where Q does not imply P. And so this whole statement is false. It is not the case in general that X being an even integer implies that X is an integer multiple of 10. So with those examples in mind, I'd like you to think about filling out the truth table for this P implies Q. So on the left, we've got all possible combinations of P and Q being true and false. And on the right, I'd like you to fill in, for each of these spaces, either true or false. So give that a pause, try that out, and we'll talk about them together. Okay, so if P is true and Q is true, then yes, P was true and it implied Q, which is true. So yeah, no problem here. If P was false, but it implies something that's supposed to be true, then this is a problem, right? A true statement implying a false statement, that is going to be false, right? So what if P is false? So if P is false, what does that tell us about P implies Q? So for a lot of people, this is a little bit trickier. Let's think about it with this example. So let's say I make the statement, if I go to the grocery store today, then there will be ice cream in my freezer tonight. So if I go to the grocery store and then there's ice cream in my freezer tonight, great, the statement I made was true. If I go to the grocery store today and I don't have ice cream in my freezer tonight, then the statement I made was false. What if I don't go to the grocery store? So if I don't go to the grocery store, does that tell you anything about whether or not there will be ice cream in my freezer tonight? So say I don't go to the grocery store, and then there is ice cream in my freezer tonight. Well, that could still happen, right? Maybe there was already ice cream in the freezer, maybe somebody else got it for me, whatever. But I said, if I go to the grocery store, then there will be ice cream. this statement is still true if I did not go to the grocery store. So basically think of this as like a promise that is made, and this promise is saying, if the first thing is true, then the second thing must be true. And if the first thing is not true, then all bets are off. So, if I do not go to the grocery store today, it could also be the case that there is no ice cream in my freezer. That would still be a true statement as well. So this is a promise where if the first piece is true, that means the second piece must be true. If the first piece is false, then the second piece could be anything. This second piece could be true or false. As just one more example, say that a candidate claims, if I'm elected to the Senate, I will pass financial reform. So again, if they're elected and they pass financial reform, great, that was a true statement. If they're elected and they do not pass financial reform, they lied. And if they are not elected, then, the first piece of this was not fulfilled. And so they can neither, in either case, no matter what happens after that, the entire statement is true. They did not make a false statement because they said, if I'm elected to the Senate, then I will pass financial reform. They were not elected. And so this entire statement is true regardless of what happens over here. So in general, the statement P implies Q is only false in one scenario. It's only false in this scenario where the first piece is true and the second piece is false. So this idea of if P then Q or P implies Q is all over the place in mathematics. Like every theorem or many theorems that you've heard stated, like if a function is differentiable, then it is continuous, and so on. Many theorems that you've heard are of this form. And so we want to talk about just different ways that is phrased. So sometimes it's phrased P implies Q, or if P, then Q. But it can also be stated as things like Q follows from P. So the fact that Q is continuous, or the fact that a function is continuous, follows from it being differentiable, for example. Or Q is true whenever P is true. A function is continuous whenever it is differentiable. P is a sufficient condition for Q. So in other words, knowing that P is true is sufficient information to know that Q is also true. As an example, let's say to pass a course, it is sufficient to get an A on the final. It's not a promise about this course in particular, but suppose that some instructor gave you this piece of information. To pass the course, it is sufficient to get an A on the final. So in other words, getting an A on the final implies that we pass the course. So this is P, and it is sufficient for Q. Here's another way we can phrase this, or another phrasing. Q is a necessary condition for P. In other words, for P to be true, it is necessary that Q is true. So an example here, again, not a promise related to this course, but taking the final is a necessary condition for passing the course. Say that statement was made. Necessary condition for, now this is P and this is Q. So taking the final is a necessary condition for passing the course. In other words, if you do not take the final, then you are not going to pass the course. So taking the final does not guarantee that you pass the course, but it is a necessary condition for passing the course. So if you pass the course, that implies that you took the final.